Welcome to the third talk of the afternoon session of PyCon. The talk title is How and Why Python is Being Used by the Military to Model Real-World Battlefield Scenarios. The speaker is Mr. Eric Silverman, who happens to be my boss. Eric's my project manager for Alitech at White Sand Missile Range in New Mexico, and he's an excellent mentor. Please welcome Eric.
Thank you. As Carl mentioned, my name is Eric Silverman, and I'm a defense contractor. I work on projects for the U.S. Army. And as he mentioned, as you can see on the big screen, I'm here to talk about the military's use of Python for modeling battlefield scenarios. Now, we work out of the New Mexico desert at a secure military installation on classified projects, and I mention that because what I'm going to be showing you today is very high-level, watered-down general information. And I apologize ahead of time if what I show you in the next half hour totally underwhelms you. But I hope you understand that while I like my job, I love my freedom, and if I go back to work on Tuesday after showing you what the Army really studies, I'll lose my job and probably my freedom as well. So your understanding is appreciated. Carl also supports the Army's Training Doctrine Command, which is known as TRADOC. More specifically, we work for TRADOC's Analysis Center, or TRAC. Now, contrary to popular belief, the Army actually puts a lot of time and effort into studying new weapons, vehicles, and equipment before they spend millions, if not billions, of taxpayers' dollars on testing and building the new weapons. And a lot of the work that's concentrated on analysis of advanced concepts and requirements is done by the analysts at TRAC. And one of the ways the Army conducts these analyses is with computer models. Modeling combat scenario always starts with what we already know, and the nature of this information is either based in physics or it's validated quantifiable data. For example, based on the size, shape, and velocity of a projectile, we know how far it's going to fly in a gravitational and atmospheric environment. So our scenario developers start with developing their scenario and plugging in the known data before they run it. Now, Combat 21, the wargaming model that we support, uses what's called a stochastic analysis system. It's very sophisticated, and it manages the interaction between the entities on the game board. Combat 21 is also what's known as a closed-form model. What that means is all the parameters and scripts have to be developed and written before the actual scenarios ran through the computer model itself. This is where Python or Jython comes in, but we're going to talk about that in a few more minutes. Now, after the model completes its run through the scenario, the output is a large quantity of raw data, and the military operation analyst, our end users, study, evaluate, and scrutinize gigabytes worth of data, from which what they create are actually the reports and briefing materials that the U.S. Army decision makers use to make their decisions in the future. Now, I'm going to start out by showing you a simple example of a battlefield scenario, and it's very, very simple because of the time limitations. With 30 minutes, I can't really show you a complex battle scenario. Also, I wanted to warn you about the video feedback that we have in our model. It's very rudimentary, so I hope you didn't come in here expecting to see Halo. There's no cool 3D graphics and explosions here. The power of Combat 21, again, is in the stochastic analysis engine and definitely not the video feedback. Now, a scenario without Python uses what's called a scripted or a static behavior, which means every aspect is known, is planned out, and meticulously scripted. Now, the first element of a scenario is the terrain data. This is a representation of an urban area. We have our roadways, buildings, which are those black squares you see up there, and to some degree a city grid. Now, we do play height in the model, but this is a top-down two-dimensional display, so it might look like an airplane's rolling along a highway, but in fact it's flying above everything else. In this scenario, we have 7 total entities or agents. We have 6 good guys. They're in 2 units, one to the northeast and the other one, the northwest, and the other one to the south. In combat scenarios, the good guys are always represented with the color blue, and we have only one red guy. He's up north and clustered inside of the city. Now, for this to work, we have to script out everything to include engagement behaviors that tells it what weapon and what target to shoot at and exactly when to fire. We lay down routes and script the maneuvers. And then we have to test the scenario. Every aspect of the timing has to be tested and ran through, or else the scenario doesn't work. So what you're going to see here is the red entity is going to fire a mortar at the blue units to the south. The blue units on the west are going to move eastward in order to capture or engage the hostile entity. And the route it's going to take, you'll see actually two different routes laid down, and the reason for that is because the U.S. Army always outflanks the enemy. Unfortunately, our red guy is going to flee the scene and escape. And the blue stops here, and it stops because there's no scripted behavior to tell it what to do and when to do it. There are obvious shortcomings for this approach, but rather than to sit here and talk about what we cannot do with scripted behaviors, I'm going to show you the same scenario that we've enhanced with dynamic behaviors. Now, when we make a shift from a static to dynamic behavior-based scenario, we have to add a couple of objects and remove some. But we're going to start with the same number of good guys, so we got the 3 up top and the 3 below. We're going to, however, add a new bad guy to the south. He's going to be in the cluster of new buildings. And what his job is, he's called the spotter. And rather than our shooter just arbitrarily shooting when we tell him to, our spotter is going to sit, wait for the enemy to approach. In this case, the enemy would be the blue force. He's going to relay the location and the movement of the hostiles over to his shooter, and the shooter will then trigger an engagement behavior. Now, there are no pre-planned routes. However, what we are going to do is designate high-risk areas, and that's why we had that red box on the highway up north. Common sense leads us to believe that soldiers in a war zone are not going to walk around in the open, so we're going to tell our entities to avoid this open area. Other than that, we want you to make up your mind and go the best way it takes you to get to your objective area. Now, the patrol unit to the south are going to move northward on the MSR, or the main supply route, what we civilians call a street. Our spotter is going to see the hostiles, and he's going to send the location over to a shooter, which will include the direction of movement and the rate of movement. The shooter is going to receive the location to fire on, and then an engagement behavior is going to be triggered. Now, in the real world, people tend to move a lot, specifically when they're getting shot at. So what we need is a formula to calculate where our target's going to be when the round actually impacts the ground. If we shoot where the target is while they're moving, we're obviously going to miss. This is what's called leading a target. Now, using a device that's available to our troops, the source of indirect fire can be accurately detected. Indirect fire, by the way, is when our shooter doesn't actually see its target, it just knows the location and lobs the mortar or whatever munition round happens to be at that particular location. Now, if you notice, we have a new object on the playboard. It's a waypoint marker, which with the location known, our support unit can now create their own route to their objective area. Again, they're going to be using a flanking maneuver. Now, with intelligent agents, they can stop moving if, say, for example, they have intel that they can receive more information while en route. So this is just one example of why Python is so valuable to us as a tool. In a scripted behavior, if we say move here, we can't do anything till the entity or the agent actually gets to its destination. Unlike that, with Python and dynamic movement, we could stop maneuvers in midstream. Now, agents with situational awareness can also stop and create their own route to the new objective. So we're not, again, having to pre-plan the route for them. They know where they need to go, they create the route, and they go there. Now, after the interrogation is actually complete, they're going to move on to their original route with a brand new route and maneuver order. Now, we also apply Python and thinking logic to the bad guys as well. So instead of our red unit just fleeing its tactical site just because we told it to, it's actually going to maintain its position until it feels threatened. So in this instance, our shooter saw that it was outnumbered by the blue forces, therefore took evasive maneuver reactions and moved. And we can continue on this scenario and talk about how our friendly forces might pursue an escaping hostile entity, but I think you got the idea at this point. Now, the big question is, why is this relevant? It's kind of cool that we plugged Python into a model and did all kinds of cool stuff to it, but why did we want to do it? And I think President Obama in August really made the best argument for us when he said that most of our defense establishment is still focused on Cold War doctrine and weapons. And 20 years after the end of the Cold War, that really is irresponsible. And scripted behaviors, they're great. They have their place. Say, for example, if we wanted to model trench warfare circa World War I, or even as recent as an armored battalion that's exercising a pincer maneuver in the oil fields of Kuwait. All those things are kind of static. We know it's going to happen, and it makes sense to do it in a low-threshold scripted way. However, when we're dealing with enemies and what's called IEDs or improvised explosive devices that really apply to no rules of engagement, what we needed was a computer model that was more flexible, agile, and adaptive. So what we actually needed from our model was a model that had a Jython API implemented. Now, Combat 21 has that Jython API implemented, which allows users to create movement and actions of entities. And entities can be anything from a truck to a tank, an individual soldier, airplane, or civilian. And with Jython, we can create very quickly these dynamic behaviors and implement them into the scenario. And with Jython, an added benefit was allowing the entities to have the Jython namespace and carry it throughout the scenario. And this represents to some degree memory and situational awareness, which again allows us to model real-world soldiers a little better than we had with the static or non-thinking entities. And Combat 21 has what's called event triggers, and what that does is an event will trigger a behavior from an entity. That entity starts reacting, and its behavior then triggers another entities, and we have kind of a cascading effect of dynamic behaviors throughout the entire scenario, which again helps us to make a lot more realistic scenarios for the Army. Now, Python provides untethered access to all the Python, Java, and Combat 21 source code, which is obviously very powerful, but it's also very dangerous. It gives the end user access to all the objects' source codes, particularly the getters and setters. So to protect the source code objects, we created Python wrapper classes, through which we give the end users full access to all the getters and a select few setters that we deem to be safe enough for them. We also have a function library that provides useful and time-saving callable methods. So using the encapsulated methods, users develop dynamic behaviors by importing the .py files and the methods and properties that we've allowed for them to use. So here's a simple example of how dynamic movement might be scripted with Jython in Combat 21. First, we import our function library on line 3. Now, at risk of offending some of the OOP gods, we decided we're going to go with an easier, more understandable, callable architecture. And I'm going to explain why we went that way in a few minutes, so if you're getting ruffled because we didn't really go Pythonic on you, I apologize for that. Now, on line 5, we use the location wrapper class to call a getter, and that way we can return the entity's current location. And what we're doing with this is actually instantiating an object from the source code, the Java source code, in the Python or Jython behavior script. With the local variables, then, we just start looping and checking for line of sight in 5-meter increments. By calling the isLineOfSight method, line 13, we can test 2 points, and when the line of sight fails, it's just going to break out of the loop by itself. And with the location of me object, which we got on line 5, we can now access the object's properties and methods. One such method might be getOffsetLocation, and that allows us to create a brand new object just by passing in 2 properties. One would be direction, and the other is the distance to the offsetted location. With the different wrapper class command, we create a new object called moveOrder. This is line 18. This object obviously has its own properties and methods. On line 20, we add the location to move to, and we also add the speed of movement that we want our entity to move on. And with line 24, again, we call the command wrapper class, but this time it's to execute the behavior that was just created. So with just 13 lines of Python code, we created a framework for coding dynamic movement without a pre-planned route. And it's only 13 lines because I subtracted all the inline documentation, so that's why you see the number 24 up there, obviously. So here's an example of how the behavior would play out in a real scenario. We have an entity that's going to be moving eastward until it hits an obstacle. So we test for line of sight from the entity's location eastward in 5-meter increments. When the line of sight test fails, the looping stops. The entity uses the distance to the last successful line of sight check, creates a move order, executes it, and ends up where it's going. Now, something that's not talked about, or we didn't talk about, or I didn't talk about, I should say yet, is who's creating the dynamic movements with Jython for us. Now, for the most part, it's the research analyst with very little programming experience. That being the case, a lot of support needed to be provided for them. Now, to start with, very detailed user documentation was written and is maintained on an internal wiki. Because they're not seasoned programmer, Java doc-style documentation wouldn't fly. So what we had to create was documentation with a whole lot of descriptions, explanations, examples, and even screenshots if we thought that it would help the end user. Also, the developer group created a training program that was about 3 workdays worth of hands-on training. It started with simple topics like basic syntax and ended up with more complex topics like how to use a database and even class files for the more sophisticated behaviors. Now, training did have management support. This allowed the developers ample time and resources to create their training. It also allowed the users time away from their daily duties to attend the training. Now, management support is something that cannot be undervalued. The actual implementation of the API into the source code, that was easy. That was a grassroots effort a couple developers took upon themselves. They created the initial proof of concept dynamic behaviors and showed everybody, and everyone said, wow, that's cool. But we couldn't have actually implemented it into the workforce if we didn't have senior management buy-in. Now, equally important is continual support for the users. Again, they're not seasoned programmers, so they needed a lot of help. Now, we could have easily just provided them the most comprehensive documentation, given them the best training, and said, that's good enough, and walked away. But if we did that, this implementation would have died in weeks. So what we have to do is actually help them out quite a bit. A lot of hand-holding is needed. And the support comes sometimes as simple as how do you compare a returned object to a string value, and other times it takes us as much as 3 to 4 weeks to create brand new complex behaviors for them. But when we do something like that, the goal is always turnkey code so that we develop the initial behavior for them, but we turn it over to the users and they maintain all of the changes and the behavior by themselves. The point is, the successful implementation of an open source solution at the user level requires that we, the developers, respect the users for their strengths and compensate them for where their strengths are not. Now, in summary, weapons, vehicles, equipments, and to some degree tactics are being used by the military were tested initially in agent-based models, some of which leverage the open source and object-oriented power of Python to develop dynamic and reactive behaviors, which, as I've mentioned a number of times now, are created by non-programmers. Now, our organization successfully implemented a Python solution because, number one, we created control access to the Java-based source code. The programmers assisted the empowered users with documentation, training, and a whole lot of support. And finally, there was a lot of top management level support for the effort. So I'd like to thank you now for your time and interest in how and why the military uses Python to model battlefield scenarios. If you have any questions, we'll have time for a quick Q&A. Also, you can take down my contact information. Feel free to ping me with any questions, comments, more information. I'd be happy to help you out at any time.
Time for a question? Howdy, I was just curious, did you, as Alitech, did you bring Python to the Army in this bid, or was that part of the RFP? Was the requirement to use Python already in place when you came to do this?
It's a very good question. The short answer is Alitech brought it to the military. They already had the model in place, and at a meeting, some of our developers that predated me plugged it in themselves and then kind of pushed it as an initiative, so Alitech actually did the implementation.
Can you talk a little bit about what drove the choice of a stochastic model as opposed to one of the other?
Stochastics is, and I'm by no means a statistician, so if there's a math major in here, please forgive me, but it's to some degree figuring out the advanced and complex statistical probability of events happening and how they affect each other. Now, there are other models that are, for example, a weather model that you see the weathermen use are called predictive models, so they run it through the model and then they predict what's going to happen. Combat 21 is not a predictive model, it's an analysis model. So what that means is we run it through, we crunch the numbers, and from there we analyze the cost-benefit of a particular product.
The animations that you had in the presentation, were those generated in Python? And if so, what libraries did you use to generate the animation?
It was created initially in Combat 21 with the Jython API, but because of security reasons and my fear of losing both my job and freedom, we duplicated all of them with PowerPoint and animation, but it was pretty much exactly how it looked on the playback.
He's a little bit paranoid, but he's protecting you. Just trust him.
You mentioned the necessity of the management support. Could you tell about some of the steps how you got that support?
Again, unfortunately, it predates me, so I don't have firsthand knowledge on how it did it. But the short answer is that the U.S. government, like the commercial world anymore, is very low on resources. And we need to do a lot more with a lot less. So the argument was essentially, instead of using an in-house scripting language, we could use Python, we could do the plugin, we could do the documentation, and therefore the analysts can do their own advanced their own advanced behaviors, and they don't have to come to a developer to create a brand new class or method in Java for them before they could start their work.
So it was money.
Which was, yes, it always comes down to the bottom line, yes, sir.
From this experience, did you get any estimate of how much time was saved, or conversely, how much increased productivity there was from using?
I wish I could say yes, coming from corporate America. However, the government doesn't really operate that way. So they said, that sounds like a good idea, let's do it, and not look back. So I'm afraid I don't have any good quantifiable evidence on the benefit we reap from it.
Did you have any resistance to implementing Python, and if so, how did you overcome it?
Yes, we did, and to some degree we still do, to be brutally honest with you. And that resistance comes from a handful of the analysts who claim they're not programmers, didn't sign up to be programmers, therefore they should not be programming. How do we overcome that problem is we do a lot more work for them than we do the analysts that say, hey, this is kind of cool, fun, and empowering. And so, like any effort in any organization, you have the Pareto rule where you're providing 80% of your support to 20% of the support class, and that's kind of where we are, and that's how we deal with it.
We still have a minute or two. Any other questions? Or are we all set? There's going to be food in the break then. Thank you a lot for your attention.